Educators have long relied on whiteboards to bring abstract ideas to life, drawing trees, flows, networks, and processes that help students visualize complex concepts. But creating clear, accurate diagrams in real time while speaking is no small feat. It demands intense cognitive effort, juggling verbal explanation, spatial reasoning, and visual precision all at once. The result? Incomplete sketches, inconsistent layouts, and diagrams that leave students guessing what's missing. When learners must mentally reconstruct what's not drawn, comprehension suffers. They're forced to decode ambiguous lines, infer relationships, and fill in gaps, effort that distracts from understanding the core idea. What if the whiteboard could anticipate what you're about to draw? What if, instead of waiting for you to finish, the system listened to your explanation, understood your intent, and offered intelligent, real-time suggestions, accepting them with a single keystroke? That's the vision behind DrawDash, an AI-powered whiteboard assistant that transforms diagrammatic teaching through proactive, multimodal collaboration. Inspired by the success of code completion tools like cursors, tab, model, DrawDash adopts a similar interaction paradigm, but for visual learning. It listens to your spoken explanation, detects your intent, and dynamically suggests refinements, completing partial structures, aligning nodes, labeling components, or clarifying relationships. And when you're ready, you accept the change with just one press of the tab key. This isn't just automation. It's agentic collaboration, a shared cognitive space where human intuition and AI reasoning co-create meaning in real time. We built DrawDash as a full-stack system integrating speech-to-text, visual analysis, and generative AI. At its core is the tldraw SDK, a high-performance infinite canvas that supports real-time drawing, undo, redo, and layering. When you speak, our system transcribes your words, identifies key concepts and relational cues, like less than, goes to, or then, and triggers a refinement cycle. A snapshot of your current diagram, paired with the transcript, is sent to the Gemini 2.5 Flash image model, Google's ultra-fast multimodal AI. This model generates one or more improved versions of the visual, which are previewed instantly. You tap tab to accept, and the update becomes part of the canvas, preserving your original sketch while enhancing clarity. Now let's see how this works across 4 real-world teaching scenarios. Case 1, binary search tree, computer science. You begin with a root node labeled 50. As you speak, we'll insert 30, it's less than 50, so it goes to the left. DrawDash detects the hierarchical structure and relational language. It doesn't just add a node. It aligns the tree, adjusts spacing, corrects edge angles, and improves label legibility. The result? A clean, balanced binary search tree that matches pedagogical best practices. The system isn't inventing content, it's refining it. It understands the rules of binary search trees and applies geometric consistency, making the visual logic instantly apparent. Case 2, HTTP request flow, web development. You sketch a browser, draw an arrow to a server, and say, the browser sends a request. The server processes it, maybe queries a database. DrawDash recognizes the sequence. It standardizes box placement, adds directional arrows, labels components clearly, and structures the flow. But here's a caveat. It introduces a large wraparound arrow from browser to database, an indirect path that wasn't intended. Why? Because the model inferred a relationship based on context, but couldn't distinguish between direct and indirect dependencies in a multi-step process. This highlights a critical challenge, semantic precision in relational inference. It's not enough to detect entities and sequences. The system must understand causal and data flow hierarchies, especially when directionality matters. Case 3, photosynthesis biology. You draw a leaf, say, plants use sunlight, carbon dioxide, and water to make glucose and oxygen. DrawDash interprets the conceptual diagram. It expands the leaf into a full process map, adds directional arrows for inputs and outputs, inserts icons for sunlight and glucose, labels CO2, H2O, glucose, and O2, and even creates an inputs-outputs summary box. The layout is clean and balanced, pedagogically strong. But notice, some text labels overlap with arrows. This is a known limitation in automatic layout generation. While the AI understands the what, it still struggles with spatial optimization, particularly in dense visual fields. Future versions will integrate adaptive placement algorithms that consider label size, arrow paths, and visual density. Case 4, heating liquid in a beaker, chemistry. You sketch a beaker with liquid, insert a thermometer, and say, now imagine heating it with a Bunsen burner. As temperature rises, bubbles form, this is boiling. DrawDash identifies the experimental setup. It adds a Bunsen burner with a flame, draws rising vapor bubbles, labels the heat source, and includes a causal chain. Heat right arrow, liquid boils, right arrow turns into vapor. But here's a subtle issue. It simplified the thermometer, removing the scale and temperature indicators. The original sketch had fine details that conveyed measurement precision. The AI prioritized clarity and completeness, but sacrificed structural fidelity. This reveals another tension, preserving user intent versus enhancing generality. In scientific diagrams, precision matters. A thermometer without markings isn't just less detailed, it's potentially misleading. So what are the broader implications? DrawDash is more than a tool. It's a prototype for a new kind of agentic learning companion, one that doesn't wait for commands but anticipates them. It draws from decades of research in multimodal learning, cognitive load theory, and interactive AI. Studies show that progressive drawing, revealing content incrementally, boosts engagement and mental model formation. When you speak and the diagram updates in sync, you're not just explaining, you're co-constructing knowledge. This mirrors how humans naturally teach. We speak, gesture, sketch, pause, refine. DrawDash tries to match that rhythm, using AI to reduce the cognitive load of visual construction so instructors can focus on conceptual clarity, not mechanical drawing. But it's still early. Our demonstrations are illustrative, not conclusive. We haven't yet conducted controlled studies with educators or students. We don't know how it affects teaching efficiency, student comprehension, or instructor autonomy. Technically, the system relies on simple heuristics, speech pauses, and visual stability to trigger suggestions. That may not align with natural teaching rhythms. It performs best on structured diagrams, trees, flows, networks, but struggles with open-ended or abstract concepts where multiple valid interpretations exist. And errors? They can cascade. A misrecognized word, a misparsed sketch, a flawed inference, anyone can lead to a suggestion that distracts rather than assists. So where do we go from here? We're working on adaptive timing models that learn from individual instructors, how fast they talk, when they pause, how they structure explanations. We're integrating domain-specific knowledge, a biology module that understands cellular processes, a chemistry layer that respects lab safety and instrumentation. We're introducing personalization, learning from accepted or rejected suggestions, adapting to teaching style, even preserving stylistic preferences like handwriting or symbol choice. And we're exploring deeper questions. How does proactive AI affect teaching agency? Does it empower instructors or create dependency? In remote learning, could it help tutors explain complex topics without a shared whiteboard? Long-term, we see DrawDash not as a standalone tool, but as part of a broader ecosystem, like how code completion transformed programming. Just as developers now expect instant, intelligent suggestions, we envision educators expecting intelligent, real-time visual assistance. Imagine a future where the whiteboard isn't a passive canvas, but an active collaborator. Where every spoken word triggers a visual refinement. Where diagrams aren't just tools for explanation, but co-creations between human and machine. That's the promise of proactive agentic whiteboards. DrawDash is just the beginning. But it shows that the future of education isn't just smarter content, it's smarter co-creation. And in that future, clarity isn't just drawn. It's anticipated.